Hello dear friends, today we will see a topic that is how circular current carrying loop is considered as a magnetic dipole. Now first of all, whenever we have the term as a dipole, first time we should have one assumption that there must be two poles. So obviously here in the case, if we consider a circular current carrying loop as a magnetic dipole, we must consider that there should be some magnetic poles are there. Obviously in that consideration we have to assume that magnetic dipole moment, and that we have already equation, that is I into area, that we have already derived and we have accepted. So that if there is a magnetic dipole, then it must has magnetic dipole moment, and that is represented by I into area, where area is vector quantity. In the same way, magnetic dipole moment is also a vector quantity. Now before going to this, first of all, from the figure as shown above, suppose there is a current carrying loop is given with radius capital R. Suppose current I is flowing through it in a anti-clockwise direction as shown with red color. Now suppose we are asked to find out the magnetic field at point P that is situated on its axis, and suppose it is lying at x distance from it. Suppose in this assumption we consider that x is very much greater than the radius. So these all things are pre-assumptions. If these are the pre-assumptions, the magnetic field at point P is given by, that is equation mu 0 I upon 2 times x square plus r square raised to 3 by 2 upon into, here it will be r square. Now here in denominator, that is already what we have assumed, that is x is very much greater than r. Suppose this is the term that we have assumed, then we can cancel out or we can drop the r square term in the denominator, and in that case what will be our equation, that b will be mu 0 I into r square upon 2x cube. Now this is the equation when we have dropped r square in denominator. So r square in denominator is dropped. So this is our assumption that we have made. Now this will be our new equation in the condition that the magnetic field at a far distance from the loop and on the axial line is given by the following equation. Now in the same equation, now we can assume that if I want to convert this equation into a magnetic dipole moment, now as I have defined here, that magnetic dipole moment is given by I into area. So out of that I have equation, and in that equation I have already I is present. Now for the loop, what will be the area of the loop? Obviously it is a pi r square. So here in this equation, pi is missing in numerator as well as in the denominator. So if we multiply with pi in a numerator, we also have to divide it with pi, and therefore the next that arrangement of the equation can be written as b is equals to mu 0 into I into pi r square. So obviously if we have multiply with pi, we have to divide also. So our denominator will be 2 pi into x cube. So this will be our new equation, but here in this equation we can convert it like mu 0 into I into a, because pi r square is area upon 2 pi x cube. So this will be our new equation. Now in this arrangement we have the term that is I into a, but that I into a we can replace it with m. So I can write this equation as mu 0 m over 2 pi x cube. Now this equation is having some certain comparable term, that as we have already derived many times, that if I multiply it with 2 and also divide it by 2, then I can have the equation that is mu 0 into 2m. So I have multiplied by 2, so I have to divide also. So 2 into 2 pi, that is 4 pi, and already there is a x cube. So if we consider and we accept this equation as equation of magnetic field on axial line of a current carrying loop at far distance, then we can resemble this equation with our well-known equation for the electric dipole, that it can be considered that electric field on the dipole. So if we compare it, E axial line, we can say that E axial was 1 upon 4 pi epsilon naught, that was k. Then here the equation has 2p upon x cube. So it was also written as a 2kp over x cube. So this is exactly comparable with the equation of electric field on the axial line of the electric dipole. If we compare these two equations, we have some resembling terms. Now we compare them and we get the resembling term. We can say that from 1 and 2, what will be the comparatively part? That as for magnetic field, here we have the term for electric field. So if I put the term mu 0 for magnetic field, the resembling term for electric field is 1 over epsilon 0. Same, if I write magnetic dipole moment as m, here I have the electric dipole moment PE. So here we can write it as a PE, that is electric dipole moment. Then if the magnetic field B is there, we can have electric field E as here, and therefore it is very well comparable equation that we have already derived in our chapter 1. Now in chapter 1 we also derived the term that electric field on equatorial line, and that was what? That was 1 upon 4 pi epsilon 0 into P E over x cube. That can be also written as K P E over x cube. Now from this equation we can also consider that if this is for the magnetic field, what will be the equation? Then we can say that from the above comparison we can say that B on equatorial line will be, that is mu 0 upon 4 pi, because we compare that where there is a mu 0 it is in place of 1 upon epsilon 0. So here we have term of that 1 upon epsilon 0. So in place of 1 upon epsilon 0 we have kept mu 0. Then obviously in place of PE we have magnetic dipole moment M, and x cube as it is as in the given equation. So this will be the considered magnetic field on the equatorial line of magnetic dipole. So these are the assumptions for the circular current carrying loop as a magnetic dipole, and it is exactly behaving as magnetic dipole as it is comparable with electric dipole with two different values. But here we have to keep in mind that magnetic monopole does not exist. That electrical monopole, that means electron or proton may have their individual existence, but this comparison of equations shows that magnetic field is always due to the term of dipole. So that is the comparison that we need to compare. The topic that is called the magnetic dipole moment of revolving electron. Now see that electrons, protons all are called the atomic structure or a nuclear structure. If we consider that we will learn in future, that is in our chapter number 12, that there is a model called Bohr model of the hydrogen atom. It is a very popular. Niels Bohr was invented this model of hydrogen atom, in which he considered that the electron, which is negatively charged particle, revolves around a positively charged nucleus, much as planets revolves around the sun. Now the force in the former case, that is in this electron and proton case, the case of this electron and proton, the force acting on them, that is called electrostatic or the Coulombian force, while in the planetary system the force is called the gravitational force. Now how this Bohr picture of electron was established and what he did in that equation, that is our new topic. In this chapter we have seen that if a charge is moving on a circular path, then it will produce a magnetic field as well as produce current. Suppose electron is moving on a circular path in anti-clockwise direction, then if we consider that it is a positively charged center which is heavily nucleus of plus Z E charge and it constitute a current I, then we can define that I in general, that I is equals to Q upon T, where this T is a periodic time. Now here suppose electron is revolving, so we can say that it is E upon T. So this is our first equation of electric current that is established due to the motion of electron in this path. Now another equation that we know that about the speed of the electron, that velocity or the speed of the electron is distance upon time. Now again time is very clear, that is capital T, and on a circular path distance will be 2 pi r upon T. So if we make T as a subject, we can get the term that is, we can get the term that compare over here, and we can write that is, if T is subject, T is equals to 2 pi r over V. Now if we replace this in equation number 1, if we replace it over here, we can say again I is equals to E over 2 pi r upon V, that will go to the numerator, and our new equation will be for the current, that will be I is equals to E into V upon 2 pi r. Now this is our important equation. Now beneath this, if we consider that magnetic dipole moment mu L is already given by current into area. Now here in our case area is pi r square. So now if we compare this equation and the value of equation 3 is put in this equation, we will have mu L is equals to EV upon 2 pi r into pi r square. Now we want to solve this question, we have to simplify it. So here the term of pi is cancelled, and here the term of 1 r will be cancelled out. Now due to this, if we compare it, we will have a new equation for mu L. Mu L is nothing but a dipole moment. So the dipole moment is represented by EV into R upon 2. This will be our new equation of magnetic dipole moment for atomic structure. Now this is not the end of the question. Here the direction of this magnetic moment is into the plane of the paper or of our page. Now why this is so? Here the reason is that here that electron is actually the negatively charged particle. So if it is moving in anti-clockwise direction, then current constituted due to it is considered to the opposite of the motion of the electron. So in that case, current I is considered as a, as we can say, it is for the consideration of current, we can compare and we can consider it that current is supposed in the clockwise direction. If current is in the clockwise direction, then if we apply Ampere circuital law in the manner that if the currents are in clockwise direction, so we will arrange our right hand fingers into the direction of this circular path, then the right hand thumb will be directed towards the inward direction and therefore we can say that the magnetic dipole moment due to the motion of this electron will be inward into the plane. Now in this condition, if we move further, we can have also one special arrangement for angular momentum. Now angular momentum is defined as EmVr. So V and R are there, we need to add mass of electron. So if in the given question, if we multiply and divide this equation with the equation of electron mass, we will have new equation that is E by 2. Now I multiply it with Me into V into R, and I also have to divide it with Me. Now MVR is considered as magnetic dipole. MVR is considered as angular momentum. Now if I put that value in that above equation, I will have mu L is equals to E upon 2me into L. Now if I want to write it vectorially, then magnetic dipole moment in a vector form is equals to minus of E upon 2me into vector L. Now why this is so, as I have explained you that due to the motion of electron is negatively charged object and therefore this negative sign will appear in the equation 5. Now with this equation we have a new term that is known as gyromagnetic ratio. If we only consider the magnitude, then the ratio of this mu L upon L, I have to write this into a smaller suffix, so let me redefine it. Mu L over L is equals to E upon 2me. Here we have to write it in a term of magnitude only, and then this is called gyromagnetic ratio. So this is called gyromagnetic ratio. It has a specific value. It is also like 8.8 into 10 raised to 10 coulomb per kg. Obviously here E is electric charge, so it has a unit coulomb. Me is a mass of an electron that is measured in a kilogram, so this will be the value, and this is verified value for different elements. Now in the same question, what is the next portion? That even with this method we can have that atomic level there is a magnetic moment, and that can also be derived. For that we are taking the help of the atomic Bohr model, and that Bohr model for atom will also suggest us a new concept, that is angular momentum, that is in a term of that L is equals to NH over 2 pi. That is the key equation for the quantum physics. We will use this relation in our next portion. Now from the above equation we have established that if mu L is to be defined, it can be written as E upon 2 me into L. Now in place of this L, if we replace the equation 1 over here, we can have E over 2 me into NH upon 2 pi. If we simplify it, we have EH NEH upon 4 pi into me. Now this equation has a certain minimum value for the comparison. So if that is compared, if n is 1, that is the minimum value that we can take, the equation will be mu L minimum, that is E upon 4 pi me into H. Now here there are different terms. If we replace all values into that above equation, that is E is 1.6 into 10 to the power minus 19 coulomb. H is called Planck constant, that is 6.626 into 10 raised to minus 34 joule into second, and the last, that is me, that is mass of electron, that is 9.1 into 10 raised to minus 31 kilogram. If we put all this value, then we get the result of mu L minimum, that is mu L minimum is equals to about 9.27 into 10 raised to minus 24 ampere into meter square. Why this is so? Because this is also the magnetic dipole moment, but this magnetic dipole moment for n equals to 1, it is having the minimum value, and therefore this term is called Bohr magneton. So this is called Bohr magneton. So that is second term. First we have derived Gyromagnetic ratio, then here we are deriving Bohr magneton. So that is another new term that we have learned over here. Here that is another that we have derived the above equation, that equation number 5, or we can say that in a value based equation, that is equation above it is actually the spin magnetic moment of the given equation, and we have that different value for that different magnetic moment. It is given by mu L. So mu L is called orbital magnetic moment, and when mu L minimum it converted, it is called the spinning moment or the spin magnetic moment. So this is the magnetic dipole moment of revolving electron in a given atom.